Hello again, and welcome back. I hope you remember from the last lecture we talked a little bit about play, how play is defined as a free and voluntary activity that we do for no other purpose than play itself, for the enjoyment that it brings, and that it can bring us into a play dynamics where we forget about time and place and suddenly can do more than we would normally do. And one of the tools that we have to bring us into such a play dynamics, we looked at and defined as Playware as intelligent hardware and software that creates play and playful experiences for users of all ages. And this Playware is, of course, what we're going to design here. And we do that by focusing on the Playwear ABC concept, where you remember the A was for creating technology for anybody, anywhere, anytime. The B by building bodies and brains, like building hardware and software, and that should facilitate the C to construct, combine, and create. And we also talked briefly about play, how that has been studied over hundreds of years. And for instance, we went back to Vygotsky, who defined the zone of proximal development, where you would like people to develop within this zone where they get challenges that fits precisely to their level of competencies. And maybe you challenge them just 5 or 10% beyond their capabilities, so that they're challenged at the right level where it's interesting and not where it's too boring or where it's too difficult, so they become anxious. But right there in the sweet spot in this zone of proximal development. And we could imagine the Playware adapt to the level of the user automatically, since it is defined as intelligent hardware and software. Now, that kind of physical interactive Playware has an inspiration from other kind of physical interactive intelligent technology, namely robotics. And robotics can be defined in many ways, and the same goes for intelligence. Here I just take two definitions. The first one is from the encyclopedia that states that a robot is a programmable machine which autonomously, meaning by itself, can perform a number of different tasks. So it can perform a variety of different things. And it differs from a computer program by this physical interaction with the physical surrounding, in this case through the sensors and actuators. And it's interesting if we look at the definition of intelligence, of which, of course, we have hundreds of different definitions, but here I take one from the Modern Artificial Intelligence by Pfeiffer, which defines intelligence as the ability to generate a variety of behaviors while complying with the givens of the systems. So here you can say that the intelligence part is what can contribute to generating this variety of behaviors to perform a variety of tasks that we're talking about up in the definition of a robot. So we can talk about the intelligent robotic systems that we are then exploiting when creating Playware, the intelligent hardware and software to create play. And this can give an open-ended flexibility, which we can look a little bit more at if we go back in history of such robotic systems. Because if we go back in time, robots, which were developed in the modern time since the 1950s, you would, for the first 4 decades or so, you would normally think of a robot as something that you have a fixed robot shell, so to speak, that there would be an engineer who who could build a physical robot, and then we would have AI researchers to make software that they could download on the robot and then test the robot with the AI. So the robot was a fixed shell, so to speak, a physical body. Um, but then we started to do experiments, like the video here is a cricket robot that we made in the late 90s. When I was in Edinburgh, in the cage you have live cricket, male cricket singing the calling song, and the robot that we see is mimicking the female cricket. If we run that again, you can see that it's approaching the cage where the male crickets are singing their calling song. And we mimic the robot to have the same ear structures as the cricket, so that there was a correspondence between the physical body and the brain of that cricket, namely, so that she's navigating towards the sound of the calling male. So there was an interplay between the body and the brain, and not to go into details here, but just say that we matched the brain, the small brain structure, and the ear structure to fit the calling song. So we could see that there was an intimate match between the body and the brain. So there was an interplay there. To explore that further, in the mid-late 90s, we developed together with the Lego and tested these Lego Mindstorms robots as a tool to build bodies of the robots, so to facilitate that we could easily explore this relationship between the body and the brain. So there you would be able to build robots, program the robots, download the program to the robot, and then start playing with this. And this is a video is from the very first public appearance of the Lego Mindstorms robot. We made this display for the World Cup in 1998 in Paris. We made this football stadium with Lego people moving, and then the Lego robots playing a football game. You can see you have the red team against the blue team, and they're playing with the ball. So this was the very first public display of the Lego Mindstorms robots, and where we were able to easily make these things, as we have seen later on over the next 2 decades, how people can then exploit building different bodies with Lego Mindstorms and create their brains, so to speak. So in order to facilitate that even further, we can say that the next step in this is you imagine you can put processing power inside each individual Lego block, and then start, as we have on the right side, the slide here, and you can start building. As soon as you put things together, they start reacting. So you have action directly in the interaction. You have immediate feedback when you put things together. This can, for instance, result in things like self-reconfigurable robots, user-configurable robots system, as we have here on the upper left side. We created self-reconfigurable robots like the H-Run robots here that can move around on themselves to change the shape from a snake to a car to a table, whatever it may be. But that's self-reconfiguration, and that's nice in terms of autonomous robotics. But if we're talking about physical interaction and learning, and so by us human beings, then maybe the other examples are better, where we're moving towards user-configurable modular robotic systems. Like you can see the kids interacting with these tiles. We had the example of the older lady on the lower left side is when she's interacting with these light cylinders. When she puts them together, she's controlling the light in the cylinders and in the environment. So you can see how she gets interested about this, because there's an immediate physical interaction and feedback to her. Or, as you can see on the lower right, where people can immediately put the Fable robots together to create their own system with their own modular robotic system by click, click, click. They put them together and they have a robotic system. So this were just some examples of where we're going from robotics and exploiting that to create user configurable robots. But we can also see how we can use this knowledge from play creating user-friendly robots for other things. Namely, for instance, I'll give you one example here. This is a good example that may inspire you where you can go in future by learning about how to create play and playware and user-friendly system, minimal robotic systems, and exploit that further. The example I will take is for the exploitation in industrial robotics. Now, I told you that since the 90s, we've been working together with Lego on creating this kind of Lego robots. And in that work, of course, we exploited and explored how to create playful robotic systems for children, minimal robotic systems, user-friendly system, how to create behavior-based control systems, biomimetic control systems, and so forth, and exploiting the modularity. Now, I had in my group when we were doing that kind of research, I had some fantastic students who later became research assistants and PhD students and so forth. You have a picture of a couple of them. Here is Esben in the middle, and to the right is Kasper, Esben Østergaard and Kasper Støj. They went through a process like this over about a decade. When we started out in the Lego lab, they were doing their bachelor on these things with the Lego robots. They did their master thesis on this, then went a year to the United States as research assistants. Esben came back to do his PhD study on the Hydra project with the reconfigurable robots. And then he did his postdoc with the flexible robots we were creating in the project, and then later started a new company called Universal Robots. Now, the first thing, some of the things we did in that process was, for instance, as you can see on the video, this is small Capera robots playing a football game, where one of them, the one scoring the goal now, is developed as an evolutionary robot that develops by an evolutionary process by itself the neural network controller of that. And it plays in the video that we see here, it plays against a hand programmed robot. So we could see that, learn that these systems could evolve their neural controllers in a simple way, in that you have on the left a co-evolutionary robot soccer show to actually win against those hand-programmed robots. We explored these things also in the children's interaction. You can see on the image also where Esben and Kasper won the championship with the Capera robots that were developed. Also, we went to create these things with behavior-based control on the Lego robots. You can see Kasper on the top image and Esben below him controlling this Pac-Man game that we created with the Lego robots and allowed the kids to interact with it. So they went through a long process of this. We went on to the modular robotics, understanding how to use what we had learned from the Lego robots to create these modular systems, also together with Lego in the European Union project on this. And then later on, we started. I was so lucky to be able to go together with companies like Easy Food and Dancake to try in a project to create flexible robots for small and medium-sized enterprises, where we would look at how can we create adaptive system, user interaction in a simple way, much taking inspiration from what we had learned over a long time from creating playful robots user-friendly robots, minimal robots for Lego, we said, could we apply that also to this sector of flexible robots for the industry? And that was the idea. Then late after this project finished, that Esben Østergaard, together with Kasper and Christian Kassow, they took on and said, maybe we can apply that on a larger scale to industrial robotics. Take this inspiration from play and Playware playful robots, user-friendly robots, and apply that here. Because the traditional image of the industrial robots was, as we see here, big and bulky and hard robots that we could say are characterized by being large, heavy, dangerous. They have hard movements. You need a lot of control theory to understand how to control this. And thereby, if you want to reprogram, you also need a skilled engineer. And often you see that this kind of robots, they are in situations like this. You can see they are inside a cage, because if you're not careful and you're not controlling this well, they will hit you and they can literally kill you from that. So they are inside this cage. And of course, that doesn't really allow this to be applied in many different situations. It allows this to be applied in the heavy industry, you can say, but not so much for the small and medium-sized enterprises. So the new idea was here that could you create robots that instead of being large were small, instead of being heavy were lightweight, not dangerous, but safe. They would have a more soft movement. They would be more bio-inspired. They would allow anybody to program this and instruct this. They would be user-friendly and not need a skilled engineer every time you need to reprogram the robot. So they took this idea on, and they created in the Universal Robot company these robots that are so easy to program and so small in terms in comparison with the industrial robots, so safe that there's no safeguarding needed. You can just interact with them. You can just program them with a simple interface. There's no programming experience needed. And of course, that was ended up being a huge success, taking this inspiration from creating user-friendly minimal robotic systems, applying that to a new sector like the industrial robotics sector, so that they were actually able to go through this and create a $300 million US dollar business, sold for that amount to Teradyne about 5 years ago, and of course nowadays is a huge success as one of the biggest robotic companies in the world, selling all over the world in large volumes. And this is really part of what we can call the fourth industrial revolution, that facilitates that you can use robotics anywhere, that anybody can have their own essentially tabletop production in the end. And remember, this coming out of this long tradition of trying to understand playful robotics, playware, and then apply that to another sector. So we can think of, can we also apply that, or can you, hopefully, when you learn about these things and you start doing this, hopefully you can be the next one who makes a $300 million business out of this. If you start to apply these things to other sectors, like to the health sector, entertainment sector, educational sector, or whatever you may come up with, because we do believe that you learn so much about these principles here that they are easily applied to motivating people to interact with your devices, if you understand this well. So you can apply that in many different sectors in your future work life. So just to give you some ideas about Playware, we can watch this small video seeing how we are creating Playware for different purposes.
In 2002,
this here in the
entertainment robot called Vicky won the RoboCop Humanoids Freestyle World Championship. Since then, Lun and his collaborators have extended the Lego block with processing and communication power to become robotic building blocks known as the iBlocks. The iBlock allows you to program by placing them in a given combination. No need for a host computer, no need to learn syntax. A democratization of robots, you might say. The idea, developed partly with the University of Siena, is to make abstract concepts concrete. Today, the iBlock technology is used for teaching where cognitive abilities are too low or where the cultural barriers are too high. For instance, Lun's team used the iBlocks for IT training in schools and universities in Africa. Now, African users can become developers rather than just users. To stimulate this development further, Lun and his colleagues have founded East Africa's first science and business park in Iringa, Tanzania. The iBlock also makes it possible to interact with the creative musical process, even for people who don't know music well. Collaboration between Lun and World Music Award winner Funkstar Deluxe has led to Robo Music. When you combine the iBlocks, you change the music. You become an involved part. The experience of collaborating in the music during a concert expands the experience of the spectators many times. Take a look at the audience faces. They're involved. Another modular robotic device are these robotic tiles. Each sense pressure when you touch them, and they communicate via infrared to each other. One use of the tiles is to play physical computer games. Installations in so-called Playware playgrounds, in schools, kindergartens and youth clubs, have given Lun's team a chance to study the user experience. No doubt, the children become motivated to become physically active in more ways than one. Not only do the tiles function in playgrounds, they've also found their way into hospitals and among therapists. The modular robotics tiles are used, for example, with children with autism, or in hospitals, where the response of a sensory input provides healing for patients. Or what about testing your abilities as a football player, like these kids, during a national soccer match? Hit the moving target, and you might end up as your football hero, playing on the other side of the wall.
So when we're creating these different modular playware devices, we have a number of design principles that these are tools with a behavior. They're doing something, so we can program them to do something. That gives a motivation and engagement by an immediate feedback, what we would call an explicit immediate feedback. And we can create this to be adaptive. There will be a modularity and thereby a flexibility in this. And we create the robustness through a distribution amongst units. And we'll explore some of these themes in the course here, and also in the scientific articles. And one of them, you'll see there's a reference to London March 2009, where we go more into details on these different design principles, so that we understand how can we create this kind of devices, and what are the principles that you can use when you would like to create this in the best possible way. And this kind of things, of course, have a long history. If we look at Playware, what are the examples that we know? Here I just put up a number of images that you can see, that you can recognize this kind of arcade game, physical arcade game that you have tried, maybe in a racing car, or a dancing game, or a music drum game. in there, or in the arcade hall, or in your private home, where you of course have probably tried things like the Wii or Kinect, that allows you to do this physical interaction, or outside in playgrounds. We see it in rehabilitation units, in art museums, where you're interacting with the technology, where you have a physical interaction with the playful system. So if we go back in history, the first examples that we see of this kind of physical game interfaces are in the 1990s. Konami made what they call Bemani, the Beatmania series of music games, and Namco made the Taiko no Tatsujin drum games. So these were kind of the first ones which have the same interaction patterns as then became popular later on in all this kind of music interaction games like Guitar Hero, Drummania, Dance Dance Revolution, where you know the different things you have to hit is coming down on the screen, and you have to hit it on that particular beat that matches when it falls down. So this originates back from the games by Konami and Namco in the 90s, and are then taken over to all this kind of music interaction games that we know today. And then also in the arcade game industry, we saw other physical game interfaces. For instance, the shooter games with guns, and the sports games with skis, or the sports cars, or whatever you have. Then in the 2000s, we saw a number of these things, the inspiration from there, moving more into the private home, with probably the first examples were Sony, that created the iToys, where they were using a camera to detect the physical motions. The games were very simple, but nevertheless they were trying to, you could polish the screen and so forth with your hands. And then came some simple guns for shooter games, and then the private steering wheels that you could use. And Disney came up with the simple dancing mats for some Disney games, and a little later you had the plastic guitars for Guitar Hero, and similar things that we had seen before in the arcade games. And then finally, which really changed a lot, came the Nintendo Wii as a handheld game controller that has inside a 3-axis accelerometer and IR sensor to measure the motion, and by that being able to control games. And that was a real game changer, which we saw a lot of it having a lot of success by being a game engine, a game station that didn't focus so much on increasing the graphical performance, but more on introducing another interactive modality, namely the physical interaction. And that inspired other competitors like Sony and Microsoft to create their versions of this, the Sony PlayStation Move and the Microsoft Kinect. And also since the mid zeros, we saw exergaming coming, which were more looking into using this kind of physical active games for fitness and health. And we saw outdoors the intelligent playgrounds starting to come. And in the smaller scale, we saw this applied inside toys. Of course, we saw that the late 90s, the first ones were the Lego Mindstorms, but then later on came things like Skylanders that mixed the physical and virtual representation. So when you had the physical character that could represent also a virtual figure that you would move around. in terms of the exergames, here's an example that we developed. So this is for the outdoors. As an ice bear and had the sound of an ice bear. So this one for the interactive running space in parks. So you could put up this as we did here in a, let me just show it again, in a public park where you would then be able to have these tracks where you could do different things like competing on a short run, or you could have stations around in the park to make a long course around where you would have some interaction, like you see here, sound and image and measurement of your performance and so forth, to have an interactive space in a larger park space. And then of course in the late zeros and in the tens came the mobile and handheld games, like the iPhone is of course the again the game changer that moves in, where you have to begin with the tilt sensor in the phone, and later on other sensors. Also where you allow location-based gaming with the smartphone, or things like tag games. So that meant that we saw further integration in those years between the physical devices, the virtual representation, and even the network and the social network that it would connect to. So the game device becomes the integration, and the best example that we have from later years is the Pokemon Go, which again became a game changer for this kind of integration between the physical device, the virtual representation, and the network. And just to give you one other nice example here is from the University of Tsukuba, who made the enhanced touch, where whenever you, to make the interaction, whenever you meet each other, you shake hand or you touch each other, the device, the Playware, can light up and show different patterns. So you use this as a mediator for people to meet and touch, and you can create games around this, as you can imagine. So also you can, so this was where you want people to meet, and it should mediate a physical interaction. You could also say that other games you want to meet over distance. So to create social interaction over distance, one of the first good examples of this was in 2001, the New York Hall of Science. They arranged a tug of war where a team could be pulling the rope in one place, and another team of children could pull the rope in another place, in this case 13 miles apart, and they would compete against each other even though they were 13 miles apart. Another example of this was in 2010, during the FIFA World Cup, we arranged a robo soccer tournament where people were playing with the football and getting points by playing up against a wall of a Playwear device we created. They were doing that in South Africa during the World Cup, in the townships in Soweto and Atteridgeville and so forth. And at the same time, they were doing this at the municipality main square of Copenhagen, and they were doing this in Shibuya in Tokyo, and playing against each other, so they could play against each other to see how many points would they get in South Africa, how many in Copenhagen, how many in Japan, in live performances against each other, and that would enhance the feeling of playing against the rest of the world in runtime. We have the example from telemedicine, of course, as well. So we see that nowadays we have physical devices that also connect to each other up to create social interaction. You physically interact with your device locally, but then you connect up on the internet to interact with somebody else who have a device here and somebody who has a device here, and then they connect up here through the network. So these were some examples of Playware. So until the next time, I would give you this small task here. Try for yourself to think about what to you is Playware. Remember, we define Playware as intelligent hardware and software for play. But that can be many different things, as we have seen in these examples in both in the first lecture and the second one, that they can be of many different kinds. And maybe you have some even better ideas than what I have shown here, and maybe some more modern ones as well. Now we went through the history, so you can think about what is this today. And then, so I recommend that you think about that for yourself, and you find different examples out on the internet. You can find different images and videos on this, and then in a virtual forum in your group, if you're a group of 3 students, for instance, then go together by Zoom or Teams or whatever you prefer, Skype, whatever you prefer. Go in your virtual forum. Each of you can represent and present an example to each other. Then you discuss these examples together, and you choose one of them, the one you think best represent Playware. Why is this a good Playware? Why do you think this is cool? Why do you think this is fun? Why is this something we all should see? And then this one you should share as a link or a video with everybody else in the course, along with 2 or 3 lines of text explaining why you have chosen this one. So please upload that to share that with all the other people, and then we can use that to discuss further these different examples. So this is one task. The other task that I would like to give you is to go in and read the introductory articles on Playware. They are numbered 1, 1, 1, 2, 1, 3. Read this, and again, then in your group, in the virtual forum, present these articles to each other. For instance, if there are 3 articles and you have 3 students in your group, then you can say one is responsible for 1, 1, one is responsible for 1, 2, and the third one is responsible for 1, 3. Then present each of the articles to each other, just 5 minutes or so. What is it about, and what do you learn from this? And then you can do that for the 3 articles, and you can discuss the articles between each other, so that you get a grasp for what is in the different articles and why is this important to our learning here. So this is my task for you until we meet again here virtually, of course, to have the next lecture. So have good fun and think about what we have been talking about, and find some cool examples of Playware, and think about what can you do. Remember the story I told you about how students were able to take all this learning and bring it into a $300 million industry. Where could you think that you could bring this in future? So have good fun. Thank you.